So for this lesson, we're going to focus on our first unit, which is foundations of functions, but we're going to only do this portion right here, this classify real numbers. We will save the second goal for a later date. All right, so the first thing we're going to do is talk about a set. A set is just a collection of items called elements. What do I mean by that is you have this list of things. You could have a list of people, a list of places, and each of those individual people or places is called an element. An element is the individual items in each set. In our case, obviously, we're going to be talking about numbers because we're in math class, so we're going to use sets of numbers to describe things. We're going to use sets of numbers especially to describe domain and range, which we'll talk about at a later date. A subset is a set of whose elements all belong to another set. So what I mean by that is we take a chunk of the original set, we take a portion of the original set, and that is called a subset. So to give you a concrete example of this, if you've ever played pool, a lot of times people play 8-ball. The 8-ball is divided into 3 subsets. The 3 subsets are solids, stripes, and the 8-ball itself. If you've never played pool, or you don't know what I'm talking about, you start the game out by racking all the balls on the pool table. You have someone strike the balls. If one of the balls, either a solid ball or a striped ball, goes into the pocket, then that is what that person uses to eliminate off the table for the remainder of the game. So if I knock in a solid, I try to eliminate all the solid balls to get to the 8-ball. My opponent would be trying to get all the stripes off the table. The last ball that you try to get rid of is the 8-ball. If you get rid of it too soon, you lose the game. So I landed a solid in the pocket. I try to get all the solids off the table. And then at the end, I call which pocket I'm going to put it in. I try to get rid of the 8-ball. So solids is its own subset, stripes is its own subset, and the 8-ball is its own subset. Now, empty sets are sets who have no elements in them. Okay, there's no answer. So for the easiest example that you guys would be aware of is when you solved equations last year in Algebra 1, sometimes you'd get no solution. There was no valid number out there that would satisfy the conditions of that equation. So we put no solution. This is where I typically teach in Algebra 1. I had a student come back from college and say, can you show them this? This also means empty set. So we're going to talk about braces and stuff when we come together, but this is also an empty set because the braces indicate that you're talking about a set of numbers. There's nothing in it, so it's considered to be an empty set. I also want to go back and talk about rational versus irrational and talk about the different sets of numbers and everything like that. Rational numbers are one subset of real numbers, and rational numbers are numbers that can be written as a quotient or ratio of 2 integers, or aka fractions. A lot of times we forget that fractions can also be turned into decimals and vice versa, but terminating or repeating decimals are also part of that rational family. And the way to remember it is terminating decimals, they end, they make sense, they stop. So like 2.45 is a terminating decimal. It stops in the hundredths place. So that is a terminating decimal. Repeating decimals, you guys are familiar with, like 1/3, which is a repeating decimal, 0.3, repeating. That is also a rational number. They make sense. They stop. They terminate. I know you may not like them. You may not like this ugly 2 9/20, but it is a fraction. It's a ratio of values. So it makes sense. It has meaning. Irrational numbers are ones that cannot be turned into fractions or cannot be turned into quotient of 2 integers. So no fractions here. The most common irrational number that you guys have used is pi because it doesn't. It's a decimal value that does not terminate and it does not repeat. All the radicals are square roots that don't come out perfectly. So radical 6, radical 2, radical 3. Those are also irate, out of control numbers. They're irrational. So like somebody that's rational is calm, cool, collective. They make sense when they're trying to argue their point. An irrational number or irrational person is somebody that's irate. They're out of control. They're not making sense. They're not using good judgment when they're talking and stuff like that. So irrational numbers are out of control. We're going to use an irrational number when we get into logarithms. It's called natural base e. It is also a value that has a long, unending decimal value, and we'll use it when we're talking about continuously compounding interest, but we're not there yet. But that's another one that you will use in honors algebra too. We have the real number system. So the real number system contains two subsets. And we'll talk about even a larger set of numbers, which is called the complex numbers. We're just not ready for it right now. But the real number system consists of two subsets. But let's talk about real number system. So the real number system, we use the capital letter R with a double bar, and that's the symbol we use for all real numbers or real numbers. Then we go to rational numbers. Remember, rational numbers are your fractions, but they can be whole numbers too, because whole numbers can be turned into fractions as well. Underneath the rational numbers, we have subsets of rational numbers, which are integers. Integers are the family of numbers that start at, not start, but consist of whole numbers, which are 0, 1, 2, 3, and it goes on forever. And it also consists of their opposites. So -1 would be the opposite of 1, -2 would be the opposite of that one, -3 would be the opposite of that, and it goes forever in this direction as well. Whole numbers start at 0 and go 1, 2, 3, 4, and go on forever. And the way you remember it is there's a hole in the middle of whole numbers. Natural numbers start at 1, 2, 3, 4, ... And natural numbers are also known as counting numbers. Some argue that natural numbers, do you start at 0 there? There's some, you can look in different sources. This is what I use. Okay, I say natural numbers when you were little and you started counting things. Mom and Dad didn't sit you on the floor and go, you have 0 cars on the floor right now, and then they'd hand you one, you got 1, 2, 3. So they get counting numbers when you're cute little kids and you start counting for the first time. Often we don't use 0. All right, so let's talk about what symbols do we use. So we already used the R, the capital R. So we're not going to use the R again here. So this one's a little tricky, but it's not too bad. Remember, rational numbers are quotients. They can be turned into quotient of integers. So we use the letter Q for quotient. We're going to skip integers. That one's the trickiest one. We'll go down to whole numbers. Whole numbers, we use the capital letter W to represent whole numbers. We use the capital letter N to represent natural numbers. Irrational numbers, we use the capital letter I. We use the lowercase I to represent imaginary, which we're not ready to talk about right now, but I is already used, so that's why we can't use I over here. So integers is the trickiest one of them all. Rational you can justify because it means quotient. And unless you speak German, Z is not going to come to your head. The reason why we use the letter Z, I looked this up. I did not know why we use Z. It's for the German word Zahlen, which means numbers. And so that gives us a symbol that we can use to indicate that we're talking about the integer family without using a letter we've already used. So we can't use I again because of the irrational is capital I. Lowercase I represents imaginary numbers. We'll talk about that at a later date. And there's all the symbols you need. Rational means fraction. Just to kind of reiterate what that means. And then all those guys underneath are subsets of the rational numbers. If you look here, it builds up. Natural numbers are a subset to whole numbers. Whole numbers are a subset to integers. Integers are a subset to rational. Irrational cannot be turned into fraction. Cannot be fractions. All right, so let's look at this chart here. So we have this decimal number here. If you look at this decimal number here, it is terminating. It stops, right? Terminating means it stops. So we got tenths, hundreds, thousands, 10,000ths. So in the 10,000th spot, it terminates, it stops. So it's clearly a real number. It is rational because it's a terminating decimal. It doesn't fit the next three because those are complete numbers. You cannot have fractions when there's supposed to be some kind of form of a whole number, a complete number. So it's not an integer, it's not a whole number, it's not a natural number. The prefix IR means not rational. So if it's not rational and we declared it to be rational, then it can't fit this bill either. Can't be irrational when you've declared it's rational. If you look at the square root of 16, this one comes out nice and clean. So this is 4. So when it comes out nice and clean, it's definitely a real number. We haven't even talked about your imaginary numbers yet. It's clearly rational. 4 fits that list of numbers that we were talking about earlier, which is integer. It's a whole number for sure, and it's a natural number for sure. It's one of your counting numbers. And then it clearly can't be irrational when you've already declared. These two contradict each other. Rational contradicts irrational. They're opposite of each other. One can be turned into fraction, the other one can't be turned into fraction. Now, my Algebra 1 kids will declare negative 2 1/3 as an integer because they see that negative on there and they go, oh, there's a negative. That means it's an integer. No, it's not a whole number. It's not a complete number. Because of this 1/3 right here, it's not going to be an integer. But they think it's an integer because there's a negative. It's clearly a real number. It's clearly rational. It's clearly not an integer. It cannot be whole or natural. They don't even go into the negative number spectrum. And since I declared it a rational number, it cannot be irrational. The last one here, square root of 10. What number times itself gives you 10? Well, it's 3 point something, right? So this one, if you put on your calculator will terminate the decimal because it only displays so many digits. But it is not a terminating decimal. But it is a real number because it's not an imaginary, which we'll talk about later. It is clearly not rational because it does not terminate, nor does it repeat, so it is not rational. Once you've knocked off rational, the next 3 have to go. And the last one, it is clearly a irrational number. So it's irate, it's out of control, it doesn't make sense. So those are the sets of numbers. That's all you learned back in junior high. I just wanted to reiterate that. I want to make sure that you have the correct symbols that represent these because we're going to use them here when we talk about the next portion of this lesson. All right, sets of numbers. A set can be finite, like a set of billiard balls. Numbers are infinite, like the natural numbers. So we have finite sets, which mean they have a limited number of items in the set, or it can be infinite. So the counting numbers go on forever. You keep counting forever. This is just saying the same thing a different way. A finite set has a definite number of elements. An infinite set has an unlimited number of elements. We're going to stop here for this lesson and we'll come back to it and we'll work on the rest of it together in class.